Hello, good morning or afternoon or evening or whatever time it is, everybody. My name is Trey Winger. I am a postdoc at the University of Wisconsin at Madison. At least I will be for another month and a half or so, and then I'm moving to California to start as an assistant professor at the California State University in Chico, which is actually where I am right now on a house hunting trip. So I'm sorry that this talk is pre-recorded, but I just could not quite get the scheduling to work out so that I could join there in person. But with any luck, I'll be sitting on a plane responding to questions in real time on Slack. And feel free to, shoot me a message or whatever after the talk if you have any questions or if I can help with anything at all. So yeah, my name's Trey. I am interested in a lot of things related to the Milky Way, the structure of the galaxy. I think a lot about H2 regions and radio recombination lines, and I collaborate with several people in the audience there, including Joe Dawson and Anita and Beth and a bunch of other people, John Dickey, on a very diverse array of radio spectroscopic investigations of the interstellar medium. Um, a lot of it's around H2 regions. But what that means is that over the past few years, I've really developed an interest in extracting the most information that we can from spectra. And in collaborating with Joe and Beth and Anita, I've realized that there's a lot of power in what we can learn about OH spectra using Bayesian spectral line models. And so that's what I wanted to talk a little bit about today. I'll admit that a lot of this talk is kind of geared towards 21 centimeter spectroscopy, just because that's the talk that I gave most recently. But I've put in some OH stuff to demonstrate, why I think this is important. So here's an outline of my talk. I'll give a little bit of background and talk about why we need to stop using Gaussian decomposition to understand our spectra. And then I'll talk about some applications to OH spectroscopy, a little bit more broad applications to non-LTE hyperfine spectroscopy more broadly. And then I'll leave you with some take-home points to take away. So in my opinion, most of um, observational astrophysics can be summarized in this one figure. Basically, all of observational astrophysics comes down to trying to understand something about the source of radiation, the emission that we see, or to learn something about the stuff between us and the source of that radiation, the interstellar medium. And so it all comes down to trying to figure out what's happening to this light as it passes through this interstellar medium and then lands on our detector. If we're trying to understand something about the source, then we really need to understand something about the intervening medium. If we really want to know something about the intervening medium, then we need to have a good understanding of how the radiation is passing through that medium and being altered into what we ultimately see on our detector. Historically or traditionally, this has been achieved through what is known as inverse modeling techniques. And so, pardon all the math here, but I kind of want to demonstrate how we got into this situation to begin with. So the idea is if you're thinking about, 21 centimeter spectroscopy or, really kind of any kind of spectroscopy, um, you take some kind of measurement that tells you something about the medium that you're looking at. So for 21 centimeter spectroscopy, we often do what are called on-off observations. And so we'll take an observation through, some gas, some neutral interstellar medium towards some background source that's bright. And then we'll look at it at a similar position on the sky, slightly off of that continuum background source. And so this would be our off spectrum. And then from the difference between those two spectra, we can learn a lot about the medium between us and that background source. And this basically all comes down to the equation of radiative transfer, which tells us how that background emission is attenuated as it passes through some intervening cloud. But then it also tells us about how that cloud itself is emitted. And then once we have our equation of radiative transfer, we can take our on-off observations and calculate all kinds of different physics that we care about, things like the optical depth, the excitation or the spin temperature, as we call it for 21 centimeter spectroscopy, and all of the various physical conditions that we care about, the total column density, the kinetic temperature, and so on. And so here's what a typical 21 centimeter emission, this is brightness temperature versus velocity spectrum here. And on the bottom, this is an optical depth, 1 minus e to the minus tau spectrum. And so this is how, these are the kinds of the equations and our train of thought and how we kind of are thinking about understanding these spectra and the context of all of these equations through an inverse model. And so what we do is that usually the first step that we do is we assume that the line profiles, that the shape of those spectral lines are Gaussians. And so the first thing we do is we do a Gaussian decomposition. We have some algorithm that fits a bunch of Gaussians to a really complicated spectrum. And then we marginalize over, in the case of 21 centimeter, we have to marginalize over the radiative transfer effects. I'll talk about this a little bit more. And then we derive the physics under all kinds of assumptions, all those equations on the previous slide. And then it's only at the very end that we can go back and we can check to see if our assumptions that we made were valid. We can test to see if there are any degeneracies or biases in our methods. But note that that all happens kind of at the end, right? The very first step was that we fit some Gaussians. And it's not until the very end where we then go and ask, are those Gaussians that we fit, are the physics that we infer from those Gaussians that we fit, are they reasonable? Do they violate any of our assumptions or our, physical knowledge about the system? And so the problems here are, of course, well, first of all, Gaussian decomposition is known to be a very unconstrained and degenerate problem. It's really easy to fit Gaussians to a complex spectrum. They form a pretty unique set of basis functions. In the case of 21 centimeter spectroscopy, self-absorption or these radiative transfer effects are very common. I'll show you a demonstration of that in a moment. And then, like I was saying, all of these assumptions are imposed a priori. Historically, this is how we've just done it because it's the easiest thing to do. It's easy to fit some Gaussians and then apply all those equations to work backwards to derive the physics. The problems are, the first most important problem, I think, is that Gaussian decomposition is a degenerate problem. And so here are some 21 centimeter emission and absorption spectra on the top and the bottom. And then these colored lines represent a Gaussian decomposition from kind of a leading Gaussian decomposition algorithm called Gauss pi, which is claimed to be really robust to these kind of degeneracies. And, it's got very few number of knobs that you can tune. And so you're supposed to be able to get kind of repeatable decompositions if you push the same data through the same algorithm. And so I tried this on this 21 centimeter emission absorption spectra. Here on the left is a Gaussian decomposition from one of Claire Murray's papers in 2018. On the right is me fitting the exact same data with the exact same algorithm using the exact same parameters that you can use to tune this algorithm. And if you look very closely, you'll notice that the Gaussians that we get are very different. And I really don't understand why this has happened because this code is claimed to be robust to this kind of problem. My guess is that we're just running into kind of some numerical effects. The fact that we have some rounding that's happening deep within the computer, and that when you have a degenerate problem like this, those small effects can become magnified into large differences, and the result is demonstrated here. And so Gaussian decomposition is a really degenerate problem. And unless we understand those degeneracies and we can model them and propagate them through our physical inference, the physics that we're trying to derive from these Gaussians, we're going to have a bad time. Here's a demonstration of this from some of the Bayesian work that I'll talk about a little bit later. So this is a posterior pair plot. And so this shows the projections of some model solutions amongst all of the parameters of the model. And in this case, I just did a really simple Gaussian decomposition kind of thing. And the parameters that I'm showing here are the parameters of the Gaussians that we kind of think about. And so there were three Gaussians in this spectrum. That's kind of irrelevant. And the parameters here are the velocity, the center velocity of each of the three Gaussians, and then the line width, the full width half maximum of those three Gaussians. And when you see it's kind of a blob, a circular blob, that's telling you that those parameters are uncorrelated. And when you see a kind of a elongated ellipse or blob like that, that means that those parameters are very correlated. And so let's look at one of these parameters that shows a strong correlation. This is the velocity of the second Gaussian, the second component of the model, versus the line width of the first cloud or component in the model. And so there's three Gaussians. The centroid of one of the Gaussians is strongly degenerate with the line width of a different Gaussian. Of course, the line width is where we're deriving a bunch of the physics from. The centroid velocity doesn't matter so much. But what this is telling us is that the physics that we're deriving from, for example, the line width of this cloud, is degenerate with a different parameter of a different Gaussian component in the model, right? There are these degeneracies hidden in the Gaussian decomposition itself that if we don't propagate through the rest of our inference, the rest of our model, when we're deriving the physical conditions, the kinetic temperature, the excitation temperature, all these other things that we care about, we're going to get the wrong answer and we're going to really underestimate our uncertainties. The error bars that we get at the end are not reflective of our knowledge based off of the data. The other big problem that happens, especially in 21 centimeter spectroscopy, but also to a lesser extent in all other kinds of spectroscopy, are radiative transfer effects. The fact that the radiation that we see in our spectrum is the culmination of radiation passing through all of the different media along the line of sight. And so in 21 centimeter land, we often get what's known as self-absorption. You have a cold neutral cloud, a cold diffuse cloud in front of a warmer diffuse cloud. That cold diffuse cloud absorbs some of the radiation from the background warm diffuse cloud. And so what that tends to look like in a spectrum is line profiles that are not Gaussian to begin with, right? And so here on the left, this is showing an emission absorption observation towards 3C78, 21 centimeter, and the Gaussian decomposition from Gauss pi. The right here are the same data and now decomposed using this Bayesian model that I haven't explained yet, but I will shortly, don't worry, where I show in the colored lines the posterior predictive draws of the emission or absorption profiles for each of the different clouds or components of this model. And what this demonstrates clearly is that due to these radiative transfer effects, the line profiles that you get out are often not Gaussian. Consider, for example, here where this orange cloud, this orange component, is apparently in front of the red component, and so you see a small self-absorption dip where some of that emission from the red component is absorbed by the orange component, and so you don't see as much of it. And so this is a problem because if your fundamental assumption, if the place where you start is assuming that the line profiles are all going to be Gaussian, you've already started with a bad assumption, at least in the case of 21 centimeter spectroscopy. And so if you take nothing else away from my talk today, the point that I want you to take away is that radiative transfer, the equation of radiative transfer, is a forward process. There is some physical conditions out there in the universe that creates the radiation. And as that radiation propagates through the interstellar medium, it gets changed. The properties of that radiation change. And then finally, we detect it at the very end. And so if we're going to try to understand that physics through an inverse process where we start with the observations and try to work backwards to the physics of the universe, we're going to have a hard time because physics itself, the physics of radiative transfer itself, is a forward process. And so I argue that a forward model is the way to go when we're trying to understand spectroscopy, when we're trying to infer the physics from spectral line observations. If you're not familiar with this term of forward models versus inverse models, think of it as a forward model. The free parameters of your model are the physical conditions that you care to interpret. Things like the column density of the emitting material, the other physical properties, the kinetic temperature, excitation temperature, the something about the turbulence or the line width. Those are like the fundamental parameters of the model that we're trying to understand. And we do so by forward modeling from those fundamental parameters into the observations. We just apply the equations of radiative transfer. We apply all those equations from the first slide, predict a spectrum, and then compare that simulated or predicted spectrum to our real data, and then optimize this using, numerical techniques like Monte Carlo Markov chains. And so this is a little bit different. The free parameters of the model are the physics that we care to interpret, not the parameters of a Gaussian that we then use to calculate, to work backwards to derive the physics that we care about. The free parameters of the model are themselves the physical conditions that we care to interpret. And so with a forward model, we kind of think about the whole problem in the opposite sense of what we normally traditionally do. But to me, it makes more sense because it's how the universe works in reality, right? The universe, there is some material out there that has these physical parameters, and then the radiation is being transmitted through the interstellar medium and via the equation of radiative transfer. That's how the universe is working. So with a forward model, we're kind of just recreating what the universe is doing inside of a computer and then optimizing it. And so the steps for this is that you first have to parameterize your model. What physics do you care about? What do you need to include? You then predict your observations, and so you just have the equation of radiative transfer, and you directly predict your observations from those free parameters. And then you numerically optimize this somehow using, for example, Monte Carlo Markov chain techniques. The benefits here are that, this is a physically constrained model. It has to be physically constrained, assuming you put all of the physics into your model. You can't get into situations where you fit a Gaussian and then at the end you realize, well, some properties of this Gaussian are just, unphysical. Like that doesn't make any sense. You can never get into that situation because you've constrained your model to be physical from step zero, from the very beginning. This also means that all of your assumptions are kind of built into the model a priori. Sometimes you have to make assumptions, assuming that the line profiles are Gaussian, for example. You have to put those assumptions in, but you're putting them in at the beginning, and so it's very clear that those assumptions are part of the model, and you can understand how those might bias your results, your inference. And then finally, like I said, radiative transfer is itself a forward process. And so by having a forward model that does all of this, you're really able to predict the radiative transfer effects that complicate our interpretation when we do this in an inverse model. Um, so some problems with forward models is that they're confusing. Bayesian models are just kind of confusing. It's just a different way of thinking. It's got a kind of a steep learning curve. And then second is that they're computationally expensive. You have to optimize them using these techniques like Monte Carlo Markov chains, which just it takes longer. It's more computationally expensive than a least squares kind of fitter or whatever. I can't do anything about the computational expense of Bayesian modeling, but what I can do is try to make them all a little bit less confusing. And so last year I published in the Journal of Open Source Software a package called BayesSpec, which is a Bayesian spectral line modeling framework for astrophysics. The idea here was to take all of the hard work out of creating these models and just make it really easy for users to use the models to learn something about their spectra. And so the second take-home point that I want you to leave with is that there is this new tool out there that is really well documented and has lots of tutorials. And I'm here if you have very specific questions or technical questions. But here is now a tool where we can use it to robustly learn something about the interstellar medium without relying on Gaussian decomposition anymore. And so let me briefly just kind of talk about some applications of this. So the first of this OH meetings, which probably talk about OH. I'll say that I was inspired to kind of work on this entire project by some of Anita's work with Amoeba, the automated molecular excitation Bayesian line fitting algorithm. This is kind of maybe one of the first Bayesian spectral line models out there, at least kind of a general purpose one for OH in this case. The idea, the kind of some of the physics that we're caring about is we're trying to understand something about the interaction between an H2 region and the surrounding molecular cloud. And I'm sure other people at this meeting will talk about this, but there's an interesting spectral fingerprint in the OH optical depth spectrum where you get an inversion in the sense of the 1720 and 1612 megahertz transitions, where sometimes you see it in emission and sometimes you see it in absorption, and then it flips to the other side. That's called the OH flip. And I don't know the details, but it tells you something about the shocks and the interactions between the matter and the gas and blah, blah, blah. It's an interesting kind of physical situation. My interest is just, how can we actually learn the most information from the spectrum that's possible? And so what Anita did was she created this Bayesian model, and it goes through it and it fits these spectra. It makes some assumptions about the line profiles being Gaussian. But one of the things that it does that's really powerful is that it enforces the fact that this is kind of an over-constrained problem. In the case of OH, we've got four transitions, but we've also only got four states that those transitions are going between. And so this is an over-constrained problem because you know that all of the molecules that are transitioning from the upper states must be going into the lower states. And so you have this kind of detailed balance thing that you can maintain, which makes the problem a little bit over constrained. We call this the optical depth sum rule or the excitation temperature sum rule. But these sum rules really just boil down to being a detailed balance argument, the fact that we have slightly over constrained problem. So I've been working on incorporating Anita's model into the Bayes spec framework, which adds some bells and whistles and does things a little bit differently, and maybe it's a little bit more efficient and more fast. But really, it kind of comes down to assuming that the line of sight is a series of isothermal homogeneous molecular clouds. They all emit Gaussian line profiles. And then in our forward model, we can enforce the optical depth sum rule. We can enforce this kind of argument of detailed balance and then fit this model to, your OH spectra here. Um, and so talk to Anita and Beth and Joe and me about Amoeba 2 if you want to use it for your own spectra. Um, because it's a Bayesian model, you get the posterior distributions of all of your parameters. And so you can see very clearly how everything is correlated or degenerate with everything else. You get a really deep and sophisticated understanding of your uncertainties, which to me is the most important part of this. If we're going to start to make claims about what these spectra are telling us about the interstellar medium, we need to be confident that we're not being biased by an underestimate of our uncertainties. Um, so lastly, I wanted to kind of just go one step further than this OH thing because I realized kind of early on that, this over-constrained situation that we have with OH is actually kind of widely applicable to a lot of different hyperfine spectroscopy. So if anybody in the audience is interested in other molecules, here's an interesting application that I wanted to show you. So I've been thinking about this in the context of 12 CN and 13 CN at 110 gigahertz or so. And so the ratio of 12 carbon to 13 carbon tells you something about galactic chemical evolution, and it's useful for reasons like that. But really, what I'm curious about is can we measure that isotopic ratio accurately and precisely enough um, to understand the galactic chemical evolution implications? And are the error bars that are quoted in the literature realistic given all of my concerns that I've demonstrated about inverse modeling? My My hypothesis is that the answer is no. And here's why. So like any inverse model, the first step is that you assume that your line profiles are Gaussian. That's fine. But then we also have to assume something about the optical depth of the lines. But when you have a lot of different transitions like this, some of these lines might be optically thick and some of them might be optically thin. That's going to change the line ratios and kind of change your inference. But maybe the satellite lines, the faintest lines here, those ones are optically thin. And so we can make that kind of assumption. Then we have to assume something about the excitation conditions. In the case of 12 CN here, like this top spectrum, these two transitions, according to quantum mechanics, should have the same optical depth. And in local thermodynamic equilibrium, these two transitions have the same relative intensities. But you can see here from this spectrum that they don't. These two lines have very different brightnesses. And so a lot of these inverse hyperfine spectroscopy models make the assumption that the excitation conditions are constant across all of the different transitions. Or they marginalize over what are known as the hyperfine anomalies, the very small, differences in the observed line intensities compared to the expected line intensities from quantum mechanics. So there's a bunch of packages that kind of do different variations of this. The problems, like I said before, is that you have unconstrained decomposition when you're doing Gaussians. And then I'm really concerned about the hyperfine anomalies, the fact that we can see in the data that the excitation conditions are not the same for every transition. And yet, most of these packages, most of the literature, makes the assumption that the emission is in local thermodynamic equilibrium and has a constant excitation temperature amongst all of the transitions. But we just know that that's wrong. Look at the spectrum. You can just see that that's wrong. And so how does that bias your inference? That's kind of the question that I want to know. How wrong are we in the physics that we care about, like the isotopic ratio abundance, because we made that assumption? And then if you really want to like care about the non-LTE effects and like, understanding the sources of these anomalies or whatever, that's actually really hard to model. And it usually requires pulling in extra codes, things like radix to try to understand the hyperfine anomalies. And so it's hard to incorporate into, some big inverse or forward model where you're trying to fit the Gaussians and understand the anomalies all at the same time. So this is a hard problem. I'm not quite sure that anybody's figured out how to do it yet. And here's a demonstration of why I think this is actually a bigger problem than maybe we take for granted. And so here are those 12 CN on top and then 13 CN data on the bottom. These come from the ERAM 30-meter telescope. These are data that were published in a paper last year by Sun et al., 2024. And I went through that paper and I reconstructed their model. In their paper, they use these lines to derive the total column density, and then they use these lines to estimate the excitation temperature, and then they use these lines to estimate the optical depth, and so on and so forth. It's an inverse model. They fit Gaussians, they work backwards, and then they kind of estimate all of these things. Well, if you go back and you take all of the model parameters in this paper and you put them all back together into a single model, and then you predict the spectrum, right? The red line here is a predicted spectrum based off of the column density that they quote in the paper and the excitation temperatures and all of the physics that they quote in the paper. If you put all of those pieces together, you get a model that is inconsistent with the data. So you can see here that the model doesn't fit any of these lines. You can see here that the red model here predicts equal brightness temperatures for these two transitions, right? Because it's assuming local thermodynamic equilibrium, it's assuming a constant excitation temperature, but that's not what the data show. And you ultimately just get a model that's really inconsistent with the data. And that's because when you do this inverse modeling thing, right, it's easy to get into inconsistencies. You're not enforcing any physical consistency at the beginning. You're just hoping that you get a physically consistent model at the end. In this paper, they argue that there is a better way to measure the isotopic ratio. And so if they do it the old-fashioned way, which is assuming LTE and then fitting all of these lines with one of those kits, one of those toolboxes, and you get a ratio of 12 carbon to 13 carbon of 50 plus or minus 7. In this paper, they argue, well, maybe we should just look at the satellite lines, these fainter lines here at the ends of the band, because those ones are probably optically thin. So if we just consider those transitions and then calculate an isotopic ratio abundance, we actually get one that's quite a bit higher, 7D plus or minus 10. And so they claim that, that this new method is the way to go. But like I'm demonstrating here, this is an inconsistent model, and so we should be a little bit worried. And so I'm working on a new model right now, which is kind of like Amoeba 2, but general purpose. The idea is that we can take what we learned from OH, which is the thing like the optical depth sum rule, and apply it more broadly to hyperfine molecular spectroscopy in general. So the free parameters of this model are, the number of components, the number of molecular slabs along the line of sight, the column densities of each slab, but in each state, right? So we've got all these different all these different states in the hyperfine states. The free parameters of the model are the column densities, the densities in each state of the molecule. And then, of course, all of the other physical parameters. And then we can have a free parameter which quantifies the statistical deviations from local thermodynamic equilibrium. That is to say, if this parameter is zero, then all of the states are populated, assuming local thermodynamic equilibrium at a constant excitation temperature. But then because we can kind of forward model this parameter lets us measure the statistical deviations from LTE. So if this parameter is a little bit bigger than zero, then it means, the excitation temperatures are all a little bit different from the constant excitation temperature assumption. So the state column densities are all a little bit different from, your expectation from quantum mechanics. And since the excitation temperature is derived from the ratio of the state column densities, then the sum rules that we talked about with Amoeba 2 and Amoeba are enforced by design. The sum rules aren't some extra component in your model that's tying everything together. The excitation temperatures are derived from the state column densities, and so the sum rules have to be enforced by design. You're forcing yourself to have a physically consistent model by design. And so you can then fit this model to those same data. Here, the colored lines show posterior predictive samples, and so these are just realizations of the model. And you can see here that these realizations all match the data exactly because they have to. They have to match by design. And then in the end, you can then go and ask, what is the carbon isotopic ratio abundance? And you get something that's around 50 plus or minus 10, which is not so dissimilar from what you get if you make the LTE assumption rather than looking just at the satellite lines, which seems to have imposed a bit of a bias. And in fact, now we can understand where that bias comes from with the Bayesian model. It's the fact that these satellite lines tend to have deviant excitation temperatures. Those are the ones where where the state column densities seem to deviate from the constant excitation temperature assumption the most. And so, in fact, the Sun et al. Authors in 2024 thought that by looking at the satellite lines that they would be debiasing their inference, when in fact they were adding bias to their inference, because then you're making the assumption that the excitation conditions of these satellite lines are consistent for all the transitions, but without ever actually testing to see if that assumption was valid or enforced. All right, so this was a really long-winded way of saying that radiative transfer is a forward process. And so maybe we should be considering our spectral line models as forward models altogether. This allows us to encapsulate the forward physics of the radiative transfer process itself, but it also lets us do things like impose detailed balance on our molecular hyperfine spectroscopy at the very beginning. And so we can make things like the optical depth sum rule, these sum rules be enforced by design within the model. If this all scares you, that's fine. I did all the hard work so that you wouldn't have to do and think about all this crazy stuff. So go check out my Bayes spec paper, look at the tutorials and the documentations, and let me know if you have any questions about how you can incorporate this into your work. I have a bunch of applications ready to go for 21 centimeter spectroscopy for OH spectroscopy. That's amoeba and amoeba 2. I've got this kind of general purpose non-LTE hyperfine spectroscopy model that's in the works and should be coming out soon. I've been thinking about weird other applications like Faraday synthesis and radio interferometry. But really, if you're doing spectroscopy, you can probably use this tool. And it's at worst going to be just as good as Gaussian decomposition. At best, you're going to learn exactly how Gaussian decomposition has been biasing you this whole time. So thanks again for listening. Sorry again I couldn't be there in person. My name is Trey Winger, and if you have any questions, please just shoot me an email. I hope you have a great workshop. Thanks.